Hello, my name is Cody Creel, and this is my Galaxy Assessment presentation for AST322. Today, I'll walk you through a recent James Webb Space Telescope discovery, a compact group of galaxies seen when the universe was only about 650 million years old. The object is officially labeled A2744-z7p9OD. I'll explain what was observed, what it tells us about how galaxies and large structures form, and how this connects to topics we covered in class. Galaxies don't spend their time alone. They live in neighborhoods, interact, merge, and eventually fall into clusters. A protocluster is the construction site of a future galaxy cluster. James Webb Space Telescope, or JWST, is the first telescope powerful enough to actually see these early structures clearly, and this one is the most distant confirmed example so far. This system matters because it shows us an early stage of large-scale structure formation. In our course, we learned that small structures form first and then merge into larger ones. Observing a concentrated group of galaxies at very early times gives us a direct look at the process in action. It also helps us understand how the gas between galaxies changed from mostly neutral to mostly ionized, a major transition in the early universe that affects how light travels. In class, we talked about hierarchical structure. A few reminders from our module on galaxies. Galaxies form inside concentrations of dark matter, which we call halos. And over time, halos merge and grow, producing groups and eventually clusters. We also discussed how environments affect galaxy evolution. Galaxies in denser regions tend to interact more, which can trigger bursts of star formation and speed up chemical enrichment. To find this protocluster, James Webb Space Telescope looked behind a massive foreground cluster called Abell 2744. Its gravity bends and magnifies the light of background galaxies. So Abell 2744 acts like a cosmic magnifying glass, letting JWST see galaxies that would otherwise be too faint. This combination, the Webb telescope plus gravitational lensing, is basically best case scenario. And behind the foreground cluster Abell 2744, the Webb telescope confirms 7 galaxies all at essentially the same distance, corresponding to a redshift of 7.88. Saying redshift 7.88 means the light left those galaxies when the universe was about 650 million years old. The galaxies are concentrated within a small projected radius of only about 60 kiloparsecs, which is a strong sign they are physically associated rather than a chance alignment. That's incredibly crowded for that epoch, more than 20 times the average galaxy density. This isn't a random alignment. This is a real physical overdensity, a protocluster core. Compared to the average number of galaxies expected in a random patch of the early universe, this region contains many more objects, an overdensity estimated to be at least about 20 times higher. That level of concentration suggests we are seeing the early stages of structure that will grow into a very massive system by the present day. Using empirical relations between galaxy brightness and halo mass, the authors estimate that the combined system could evolve into a halo with a mass comparable to the most massive clusters today. Redshift is like a cosmic time machine. A redshift of 7.88 means the universe was only about 650 million years old when this light left the galaxies. Using empirical relations, the authors estimate that this structure could grow into a coma-like cluster today, with a halo mass around 10 to the 15 solar masses. So we're literally watching a giant galaxy cluster in its infancy. The discovery used 2 main Webb telescope tools. First, NIRCam took deep infrared images to find candidate distant galaxies. These candidates are selected by a color technique that identifies a sharp drop in blue light, which indicates the light has been stretched by cosmic expansion. Second, NIRSpec took spectra. That is, it split the light into a rainbow to find specific emission lines. Emission lines are bright features produced by hot gas in galaxies. Their observed wavelengths tell us the galaxy's distance very precisely. So here's how the Webb telescope turned these blobs into real distances. For step one, near-cam imaging picks out high redshift candidates using the Lyman break, where the galaxy suddenly drops out of the blue filters. In near-spec spectroscopy detects strong O3 doublet lambda lambda 4959 and 50007. The key spectral feature used to confirm the distance is the oxygen emission line known as O3, specifically the pair at rest wavelengths 4959 and 5007 angstroms. At this redshift, those lines are shifted into the infrared and were detected clearly in all 7 galaxies. Detecting the same spectral features at the same observed wavelength in multiple objects is the most reliable way to show they are at the same distance. These galaxies aren't giant quasars. They're more like normal early galaxies, and most have been forming stars actively in the last 100 million years. Some are surprisingly dusty, especially YD4, which has noticeable dust extinction. That means these galaxies have already formed multiple generations of stars and produced heavy elements and dust. Chemical evolution is happening fast. So now let's look at the galaxies themselves. The team used the galaxies' measured colors and spectra to estimate star formation rates. That is, how many solar masses of stars are formed per year. Most of the galaxies show evidence of recent star formation within elevated rates over the last roughly 100 million years. In plain terms, these galaxies are actively building their stellar content right now, which is consistent with the idea that dense regions accelerate galaxy growth. From the same modeling of the light, the galaxy's stellar masses are estimated to be in the range of about 10 million to a billion times the mass of the Sun. One galaxy in particular appears to be older and more massive than the others, indicating it started forming stars earlier. This diversity, some galaxies younger and actively forming stars and one more mature, is exactly what we expect in forming structure where different members have different growth histories. One of the coolest surprises is that some of these galaxies are already dusty. Dust is made in supernova and evolved stars, so it takes time to build up. And yet YD4 shows AV around 1.1, which is a lot for a galaxy only a few 100 million years after the Big Bang. This tells us that these galaxies have already gone through multiple generations of star formation, producing heavy elements and dust. It's a reminder that the early universe wasn't just pristine hydrogen, it was already getting messy. Finally, let's talk about metallicity, which is the fraction of a galaxy's material made of elements heavier than helium. The observations and modeling indicate that these galaxies are already chemically enriched compared to pristine gas. This enrichment supports the idea that star formation and feedback have been active for some time, and that these dense environments can accelerate the buildup of heavy elements. So even at a redshift of around 8 or 7.88, this protocluster is chemically evolving. Another sign that we're catching a future cluster in its early growth phase. Astronomers often use a hydrogen emission line called Lyman alpha to identify and confirm distant galaxies. Lyman alpha photons are easily scattered by neutral hydrogen, so their visibility depends on how much neutral gas surrounds the galaxy. In this protocluster, Lyman alpha is weak or not detected in most members. That absence is informative. It suggests the surrounding intergalactic gas is still substantially neutral, which affects how easily Lyman alpha photons can escape and reach us. The authors use these tight upper limits to infer that the surrounding intergalactic medium is still highly neutral, with a neutral fraction greater than about 0.45. And so this ties directly into reionization, the area when the first stars and galaxies ionize the hydrogen fog filling the universe. We might expect a crowded region like this to carve out a big ionized bubble, but the missing Gly alpha tells us the bubble isn't big enough yet. Using the lack of Lyman alpha emission, the authors estimate that the fraction of neutral hydrogen in the region is relatively high. Roughly speaking, a significant portion of the hydrogen is still neutral. The early universe in this area had not yet been fully cleared of neutral gas. This result shows that even regions with many galaxies can remain partly neutral, which tells us reionization, the process that made the universe transparent to ultraviolet light, was patchy and not uniform. So even in a dense region, the universe is still pretty foggy. Reionization was patchy, uneven, and still underway. This system neatly ties together several topics from our galaxy's module. It demonstrates hierarchical growth of structure, shows environmental effects on galaxy evolution, provides evidence for early chemical enrichment and dust production, and offers a direct probe of the reionization era. It also highlights observational techniques we discussed, using color selection to find candidates, spectroscopy to measure distances, and gravitational lensing to magnify faint sources. It's important to be clear about limitations. The sample is small, and lensing complicates the interpretation of intrinsic brightnesses. The estimates of mass and neutral fraction depend on models and assumptions. Open questions include how many fainter members remain undetected, how the system's three-dimensional structure is arranged, and how representative this protocluster is of the general population at that epoch. And future observations that would help include deeper spectroscopy to find fainter members, observations at sub-millimeter wavelengths to map dust and cold gas, and improved lens models to better correct for magnification. These data would refine mass estimates, star formation histories, and the role of such overdensities in reionization. To summarize, James Webb Space Telescope has confirmed a compact group of 7 galaxies at redshift 7.88, seen when the universe was about 650 million years old. The galaxies are actively forming stars, show signs of dust and chemical enrichment, and are concentrated enough to be considered a protocluster. The weak Lyman alpha emission indicates the surrounding gas is still substantially neutral, so reionization was not yet complete in this region. This system provides a valuable direct example of early structure formation and connects strongly to the concepts we've covered in class. Thank you for listening, and I look forward to any questions you may have.